For us as a project, it was definitely a big change because we are now in the public, in the open. This is not a technical talk. I hope to really motivate the use cases and the benefit that users, as well as admins, as well as engineers, can have from these cloud and open science ideas. Have crystallized out of a large amount of ideas that we've brainstormed, and it starts to get real this year. Teaching itself, and there are two parts in the teaching. One is we try to teach CloudNative to our fellow engineers and students, so understand where are the concrete use cases, both in research as well as in teaching, where we can help, where we can interoperate, where we can collaborate, and to build those out ideally together. Here, primarily, we try to not care who you are, where you're from. The only thing that we hope is that you find in our stack or in our approach something that you like to contribute, and that ideally is what you can do no matter where you're from. The focus of this example is how to do open science. So they are a research group, they are primarily physicists and mathematicians, and we as engineers wanted to see how can we collaborate and how much effort is that. To teach students what cloud native is, what is DevOps, and also why is cybersecurity so relevant in today's world. Here we have, I think, not just in Austria, but everywhere, a tremendous lack of trained workers. Why not just teach it? And here use gamified exams as to have a means, a platform to test real practical skill and knowledge in an exam, rather than multiple choice or any of the other, let's say, a bit more traditional approaches. And then the last part is, so we've open sourced something and possibly you're interested in it. So how can you get involved? What is the benefit from universities, and where are we? How can you interact with us? Is a lot more money efficient to share these infrastructures and to learn from each other, and also to exchange. That whenever we make something open, but it's not just like, let's say, code itself, but we want to have an actually live environment that I want to share with someone else. We have the issue that these live environments tend to be exploitable. It's cost efficient, but still within a risk profile that we can accept. Then in the middle, we have these sort of packages. One is this fish-like one, which is a container. It symbolizes a. Maybe you know that we have a high-performance computer here in-house, which belongs to many Austrian universities. It's called the Vienna Scientific Cluster. The project is, how can we make high-performance computing more interactive, easier to learn, shareable, and fair? Is really, how do we translate this knowledge, this accumulated knowledge from one person's head to another in the easiest way possible? And that's because I used to work in HPC myself. So the code maintainers of these code bases are oftentimes not incentivized to do fair and open source. They are often incentivized to publish papers on their core research. What we want to achieve here is the portability and the translatability. And the first use case that we want to implement is a so-called paper companion. And if you've ever visualized 3D data, you know that it's very, very hard to choose in a paper where you have to pay for each color figure, which slice, which viewpoint you display. It could be much more insightful to give someone the ability to turn a 3D figure around, or to plot the different density from color gradients. That could make it a lot easier for peer reviewers to judge the scientific method is legit, like the laptops and making things run and dealing with scripts until finally hours later you can just get started with the teaching, just to save that time. We are not expecting anyone to run actual performance in these labs. They're really for toys, review, or learning. It's a web service platform where we can, via the browser, present an interactive environment to a user. And Jupyter Hub gives us the ability to do this in a multi-user fashion. You can select whatever the admin shared with you in this case, and you see you can choose a particular image version, and then you get a resource quota, in fact, that the admin makes available to you. And here we have an example, which I hope is in the video, that some students at TUV programmed a grader extension. So, and the cool thing for us is basically we control the application. The user only needs a browser, and we can also extend it with these fancy features, such as in this case, the grader. Or when I speak about the layers, I typically think about three. So there's the data center itself, which I don't consider to be a layer. This is just somebody has hardware and typically cooling and electricity and all that stuff. On top of that, what we do in a cloud sense is we say infrastructure as a service. So this is a cloud provider. A cloud provider can be public or private. And what this gives us is the ability to create virtual machines on demand or to create network on demand. So instead of basically plugging cables in, we do commands, or we have a browser-based interface where we can create virtual instances. But when you have lots and lots and lots of these containers, it gets extremely cumbersome to do the bookkeeping of what these containers do, how many somebody has logged out. Should we delete this container now? Should we maybe scale up because there's more load? Should we scale down? All of this orchestration that's done by the platform layer. And for that, we use Kubernetes. If, however, your expertise level is more on the application side and you want to have a new Jupyter extension and everything else you don't really care so much about, then you write a Jupyter extension, plug it onto the existing Jupyter container image, and then update what Kubernetes is supposed to schedule for you. And the cool thing is that if we do these blueprints now, a user can choose which parts they want, which parts they want to exchange, and which parts they also just want to ignore. On the other hand, we want to also make it scalable and say, well, on a research group level, we want to give you something so canned and so standardly prepared that you can self-administer a so-called Kubernetes profile. So basically, all these blue individual features become toggleable by us saying there's a profile and we call it OpenScienceLabs. Registries are the point where we share images. Images are applications that are built for this blue layer. And what we need to provide, of course, is a way for people to publish them there, and another way for users and for also the clusters to pull them from there again. So, and for that, we need identity. This means we need to have a means to identify users from different universities to be able to share with each other the same, okay, I'm Constance at TU Wien, but I'm also Constance at Universität Wien. So I'm still the same person. And then there's always the question, do I have the same access? A very important question to figure out this integrated access management properly so that for the user, for the end user, it seems smooth. And the two lower levels, so OpenStack is in this case our choice of cloud provider, is private, so we have the infrastructure here. And we use all of this automation tooling to make it scale. So we have very few maintainers that actually write this code for you. And for that, what we really need to test is all this automation that goes into hiding this complexity away from the user. And then the green layer is, for me at least, and ask questions here is relatively obvious. Somewhere there needs to be the hardware. And this can be either here in Vienna, or it can be in a public cloud provider where you've rented. We call them Pokeballs because we're extremely serious about this, to tame essentially the sometimes monstrous effort of getting these magnetohydrodynamic codes to run on a new infrastructure. And the use case that we're trying to do here is have this first interactive paper companion where we have public data. This is what we call a profile. What is contained therein is maximally hardened Kubernetes. This means a very secure Kubernetes. It runs the Jupyter. It has custom Python images in order to allow us to do this rendering, this plotting. And it is able to talk certain data mount points so that you can actually read and link to the data wherever that is externally stored. Let's say you're a research group, you think, that's kind of cool, I want to do this too. We've found that the best way of doing this is that you have one person who's really good at containerization and one person who really knows the code well. You let them sit for N weeks, and eventually a container will come out of that. It also depends on what exactly you want there to be inside the container. Sometimes you just want these rendering features, but sometimes you might also want to be able to compile your code or to debug your code. Then you would publish your image, and publish or push your image. That doesn't necessarily mean it's public to the world. It just means it's then shareable and it's deployable onto this cluster. And probably you'll have to iterate a couple of times until you really get it right. So here we see on the start, this is Jupiter. This is on our environment. This is from a couple of days ago, that a person from NCAR, from the National Center of Atmospheric Research, provided this ionospheric plot. It is from a summer school. And what is preloaded into there on the left-hand side is actual HPC data. The application, now please schedule it for me to give it to whoever has access to this cluster. And what essentially only happens, and this happens in seconds, is that this Kubernetes will change the references and allow you to consume the image. This is the code base where people are working on this magnetohydrodynamics thing. So somebody pushed a change. It's in this case, it's owned by JHU. Now this is owned by us. This is a pipeline, and this build process actually runs in Vienna on a VM. So it builds and it would test that this build is correct. Now, the third step is basically, given the right application, given the right target, the only thing it changes a profile on a cluster, and now this image is available on this cluster. That's basically how you federate it. And the key part to get right is actually access, really, and orchestrating all these federated things. Okay, data. So runtime was the part where we're plotting this object, and we made sure that all the libraries are in this immutable image that contains the application which we want to abstract. So the only thing that the user can do is plot this. You can see that there's a group share here on the left. So the point is that this data also survives for longer. So I can go from cluster 1, 2, 3, 4, 5, and maybe also a couple of weeks in between, that this shared data will stay there. So those two things, so the state, the data, and the runtime are completely separated. And also the access controls are separated. So that gives us an enormous amount of flexibility to handle these use cases. And now the question is, so how do you spread the word about HPC, get new users onboarded, new group members, new PhD students, whatever you want? Now, we talked about building being hard. It tends to have, especially in research, very specific dependencies that may not build, or even if it builds, it might not work. A small runtime, but we'll be able to, again, take away all this making the code, building the code with the right compiler. If you look at the left, you see that this is a specific version of the Intel compiler 2160 2022, blah, 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 with a particular wrapper of HDF5, blah. So this is all taken care of already, and also check that these versions match. And now students or interested users can play with the code, can see how maybe the magnetic flux density changes if you do something. See Jupyter as a web runtime with strong controls. So we adapted the upstream Jupyter, so the one that is open sourced and that many universities use it, to include different ways of handling groups. So we can do this federated login easier. When we do open science, we assume that the audience is large. And while not maybe completely public, we cannot control, we don't want to control who looks at such a runtime. So we have to really keep in mind that these clusters will have issues of being attacked from random sources, simply because they have to be relatively public, they're relatively exposed. So we have chosen to build them for compromise. The lifespans of absolutely everything that has to do with the runtime is very, very short. So we can kill something, make sure that nobody polluted this environment, or even if they polluted it completely, they get wiped, and we can reinstantiate the environment cleanly. This is, from our perspective, very, very important, especially if you're running it on a university infrastructure, because you do not want to give nasty people a way into your infrastructure simply because you're doing open science. That would, I think, really defeat the purpose. Make it low cost. So also our tool choice is that you have so many options. We try to choose things that will not incur undue cost, and also in terms of human cost, like make it easy to maintain, make it easy to read, make it simple to translate, also from mental model to mental model. that the network is segregated, meaning that people cannot break out of a lab into the university infrastructure, that people cannot use the data to access other points on clusters inside the university, and that inside this application, people are contained therein. They cannot go deeper down into these lower layers. Those are the three things we want to really ensure. And a lot of work, I would say more than 50% of our work is actually in these non-functional requirements in order to make the usability good for the end user. Give examples that work for real use cases. However, try to make it such that you can exchange individual components because they are standard-based and it will very likely still work. And for the humans to make it scalable is these train-the-trainer programs. So I think we can call this a success if we manage to expose our users only to such a small level of technical detail about all this cloud computing that within a couple of weeks, we can have researchers teach other researchers to use these open science labs, and they don't have to take a half-a-year course on, for example, Kubernetes first. Yeah, if you are interested in any of this, we are looking forward to working with other teams this year. Sometimes from despair, there come good ideas. So we basically said, well, why don't we actually teach this on a real university level course? And teach what is cloud, cloud native, DevOps, and security. So how does this fit into what we said before? So actually up to the blue layer, it's almost identical. So the only thing is that we changed is the orange layer on top, where we have a different profile now. So instead of installing Jupyter, which was the teaching, and which is interactive web shell, we now install actually a game. Maybe you remember that in the bottom there is Pac-Man. You remember this game? So it's our sample application. And this application is built with all bells and whistles attached. So basically we demonstrate all the things we want to teach on this Pac-Man application. That means we need a lot of auxiliary tools as well. And those we put on those profiles and make them installable so that once you choose, for example, the profile build system, you get this nice space dog, for example, which is called Tecton, which is a cloud native CI system. We can build these clusters, not just for researchers, but also for our own purpose. And in case we find that it's useful to teach something, we can share this in many clusters. These clusters are actually going to be very small, mini clusters to many students that live for a couple of hours. And this whole identity federation, the sharing of data that we talked about earlier, is really the same. It's just this time for university students, and we're playing Pac-Man. We're not playing Pac-Man. We are using Pac-Man as a reference application because it's very, very simple and very clear-cut to teach all the stuff around all this automation, security, policies, and certificate management, and secrets management, all these things that are on the lower level and are really important. And the idea is to do it in a gamified and playful way somewhat. We use this on-demand infrastructure with a profile, but now we also have an idea for the exams. So I don't know if you've ever heard of CTFs, Capture the Flag. So it's a children's game. It's another game. The question is, so how do you test this? How do you test that somebody has learned how to deal with all of these small applications? Well, there are one way, at least, that I think is possible, is to basically host a scavenger hunt or a interactive set of challenges where they find broken systems. They'll find different pieces of systems that are broken, and they have to fix them. And whenever they fix something, they get a so-called flag, which then they can enter into a system, and they have to write a little bit about how they found it. And so we can hopefully really test that somebody has understood how a system works, and they have this challenge-like environment online. So the other thing that I think is going to be important is to let people invent their own construct. So rather than teaching frontally with a lot of theory, the idea is let's get the students into a real life situation where they have to build an application. So, and not just build it, they have to build it, they have to deploy it, they have to host it, they keep it alive, to monitor the thing, probably it's going to die, and also to work in a team together. The teamwork aspect is, I think, today incredibly important. To just learn, so well, it was your job to deal with the network, it was my job to deal with the build process, and now it failed. Like, how do we handle frustration, blame, and how are many of these processes actually that the choices that we make that work well often have to do with the human aspects and not so much with the technology aspects. And open source often, or could be, when you start with it, you might not realize that there are actual humans behind open source projects. And this is something that I would also like to stress, is how you should interact with other maintainers when a feature doesn't work or something, or you would like to contribute something. How do you actually contribute in a meaningful and productive way to other people's source code? The way we will teach this is to have a lot of time, because we'll take 8 hours per week, small groups, and really give people a lot of time to invent their own applications, to go deep, and also to fail. So the way we want to cover theory parts is actually to build a concept completely from scratch. For example, a container runtime from first principle, rather than teaching slides so much the other day of the week. We would like to expose them to that overabundance of tooling that you find in a typical cloud stack, where then they have to find their way and build their own application up together as a team. I think it's really important to create this playful atmosphere, and to, both in the exams as well as in the labs, to create and to focus on enjoying failing. And I would say that if we get that across in the lecture, then I'll be very happy. The way to pass the class is to have both a presentation on what you learned, on how you failed well in your startup, and to also play 3 times this CTF game, and and prove that you can sort of repair a system when you find it broken in a way that you previously saw it in an exercise. Now we have something that works, right? But it's still a baby. It's still development. I really do believe in iteration and feedback and learning also from challenges. So I think that having it now out in the open, where people can say, well, this works, but that thing really doesn't work for me, or can I actually contribute my idea here? For example, you don't like OpenStack, so you want to work on Azure Cloud, or you want to work on Google Cloud because you have money there. So how would we support having this exact same user experience on 2 different clouds? It's something that I'm pretty sure will come very soon. But we want to work with actual users that actually have the need, so we can test it, not just because maybe somebody needs it. And this is why now we have this all open sourced. This is the link is going to be in a couple of slides. You can look at it. We're going to write some document, like how could that work at another institute, or what are your specifics, and how can we avoid reinventing the wheel, which I think in the Austrian university landscape, it is a bit of an issue that, let's just say we could work a bit more together. And so this is our idea, just to put it out there. And for you, if you don't like it, particularly you don't like certain aspects, for you to be able to criticize us while you can still benefit from all the other things. And so do reach out to us if that's at all of interest to you. And every Wednesday at 3 p.m, there's a completely open session where you can ask questions. You can also ask questions up front, or ask for a demo of something. Get in touch, and if you're interested, do reach out. But in any case, again, Happy New Year, and thank you so much for your time. And yeah, so I will simply leave you with the links. So if there are ever any questions, Wednesdays 3 p.m, drop us a line. And otherwise, have a great rest of your week.